Hello, everyone. Welcome to BrainMap. This seminar series is co-sponsored by the P41 funded Center for Mesoscale Mapping, housed in the Martinos Center. It is our great pleasure today to have Dr. Zhongliang Zhu from Vanderbilt University. Dr. Zhu is currently an associate professor in Vanderbilt University Medical Center. He received his Ph.D. degree in medical physics from Peking University in 2008. After that, he joined Vanderbilt University Institute of Imaging Science as a postdoc fellow and became a faculty member in 2012. His research focus primarily on the development of advanced MR sequences, including chemical exchange saturation transfer, SAST, or magnetization transfer, MT, spin lock, etc., for molecular and physiological imaging. Most recently, his interests have expanded to the innovative analysis method for fMRI signal. I would like to remind our audience to address your questions by raising your virtual hand or write in the Q&A box at the end of the talk. And thank you very much for coming today, Dr. Zhongliang Zhu, and the stage is yours.
Thank you for the introduction, and thank you for the invitation. And I feel excited to give this talk. So the title is Missing Third Dimension, Functional Correlation of fMRI Signals Incorporating Wet Matter Bundles. Both signal in wet matter has been reported for a few years, but there's currently two issues that haven't been addressed. The first issue is there's no appropriate method to process the fMRI signals from both gray matter and wet matter as a whole communication system. It's important to know that the gray matter is a signal processing unit and wet matter is a signal transmission unit. They have different functional role, and so, but currently people look at them as the same and use the pairwise correlation to process them, and this is similar to the conventional gray matter correlation, which provide network among the signal processing units. But this may not be appropriate for the communication system. Second, as wet matter is a communication unit, so how to connect it to functional communication by incorporating wet matter is still unknown. Recently, we have a paper to introduce our work to address these issues. In this work, we develop a method called triple-wise correlation, or the three-way correlation to process the fMRI signal from a couple of gray matter and one wet matter bundles. And by using this triple-wise correlation, we provide networks, which we call communication network. Our study showed that this network has different mechanisms from the conventional functional network. First, let me introduce triple-wise correlation. It is a synchronization in gray matter, wet matter, gray matter triplet, determined by creating a covariance matrix from the triplets functional time series using PCA to get eigenvalues and calculate a linear index from the eigenvalues. So here's a diagram to show the triplet, in which there is a pair of gray matters and one wet matter bundles. So here we have the yellow area, which is a common component among the three functional units. We can also call it a combination component among the three functional units. It is a communication part between this pair of gray matter through this wet matter. There's also other areas like the orange and the green areas. They are the common components between a pair of functional unit, but not among the three functional units. For the orange area, we can look at it as communication between this pair of gray matter, but through other wet matters outside the triplet, this triplet. For the green areas, we can look at it as communication between this gray matter but another gray matter outside this triplet and through this white matter. Also, there's a purple and blue areas. They have no common component between any parallel functional unit or among the three functional unit. We can look at as association between only one functional unit in this triplet, or the local functional unit that did not transmit it, or the non-functional signal such as different HRF in different functional units. And we use a simulation to study the triplet correlation. So this plot shows our simulations for a few cases. So in the simulation number 1, we simulate the situation in which there's a common component among the three functional units. It's a yellow area. We find the triplet correlation value is high. And in simulation number 2, we simulate the simulation in which there's a common component between any parallel functional unit, but not among the three functional units. We find the value is very low. And in simulation number 3, we simulate the situations in which there's no common component between any parallel function unit or among the three function units. We find the value is also very low. And in simulation number 4, where the three functional units are fully overlap, we find the value is 1. So this triplet correlation can reflect the communication between a parallel gray matter and through a specific white matter, the yellow area, but not that through other white matter, for example, the orange area. Thus, the triplet correlation may reflect the communication pathway. Okay, so we use a multigraph to describe the whole brain system. In this multigraph, we have 82 Brodmann gray matter area as nodes, and we have 48 GHEO white matter alleles. And each white matter carry 82 multiplied by 82 edges between all parallel gray matter nodes. And each parallel gray matter node has 48 edges with each through a white matter. So this multigraph model allows us to allow parallel nodes to be connected by more than one edge. So this confirms with the concept that the functional connectivity can be transmitted through multiple white matter bundles. This is different from the structural connectivity. By using this, from this multigraph model, we generate a 3D gray matter, white matter, gray matter matrix. And we use the triplet correlation to define the edge on this 3D matrix. So we study this 3D matrix from 2 points of view. First is from this 2D matrix. We call it a 2D graph. And this shows the gray matter correlation through a specific white matter bundles. Another viewpoint is in this direction. The 1D matrix, we call it 1D plot, which shows that the correlation among a certain parallel gray matters and all white matter bundles. Now let me introduce the mechanism of the triplet correlation. So just now we find that although this triplet correlation is sensitive to this common component among the three functional units, it's still skewed by other components. This may reduce its specificity to this common component. So we use simulation to study how it was skewed by others. So first, let me introduce some parameters here. So here, for the common components among the three functional units, we use I to describe it. And for the functional, the signal component in the gray matter, we use a J. For signal component in the white matter, we use the W. And we also use I and G to describe the gray matter index and K to describe the white matter index. In the simulation, we first generate a few independent signals from S0 to S3. And we then generate the synthetic signals by the sum of the S0 with any one of these three independent signals. We also add an adjusting factors to adjust the amplitude of these independent signals. So here we have the three signals. For the two gray matter and the one white matter bundle, and all this functional unit has A0, S0 that represent the common signal, and also they have their own signals. And for the signal components, the I is equal to the sum of square of the adjusting factors. So for the common component is A0 square, and for 1J, that is for this example, that's A0 square plus A1 square. So here's our simulation result. The red curve is a simulated triple-wise correlation as a function of the relative size of the common component to the whole component in a functional unit. Here in the X and the Y direction, they represent the relative size to the two gray matter areas. And for the different subfigures, it represents different relative size to the white matters. So you can also, we have a blue curve, which is calculation of the value of this formula. It's common components over functional units and product of them. And when the alpha is equal to 1/4, we find that the two curves match well. So this suggests that the true-wise correlation depend on this formula. And so we can interpret it that it shows the relative size of the common components among triplet to all the common component in this triplet. And to compare this with the conventional correlation, we also draw the diagram of the pairwise correlation. Here, Ij represent the common component among a pair of gray matter, Ij. And it depends on this formula, which shows the relative size of the common components between a gray matter pair to all the components in this gray matter pair. So this shows the mechanism of single triplet or single pairs. In the whole brain, for example, for the gray matter correlation, we usually generate a 2D matrix. So here we showed it. It reflects the distribution of this relative size of the common component to the all component in these pairs for all gray matter pairs. Similarly, currently people use a gray matter and white matter correlation to study the white matter, it similarly it shows the distribution of the relative size of these common components to all components in these gray matter white matter pairs for all gray matter white matter pairs. So for our triple-wise correlation from one viewpoint, the 2D graph, we can show the diagram as this. So it shows the distribution of the relative size of these common components among the three functional units for all these gray matter pairs through a certain white matter bundles. As we just gave the signal model that we found that its magnitude, it's scaled by the non-common components, which may reduce its specificity as this may relate to the like different HRF or local functional signals or connection with other part. So here we study how the non-common components influence the 2D graph. So here is a 3D matrix. We choose this 2D graph. We remove formatting each 2D graph to a 1D matrix. Note that this 1D matrix is 82 multiplied by 82 is different from this 1D plot. And we then get the mean and the standard deviation of this 1D matrix across all white matter bundles. And we get this plot. So In this plot, we can find the variation of the mean values is comparable to its standard deviation. This suggests the presence of the common pattern of the 2D graph across these all wet matters. So here, note that this only shows the first 82 pair of gray matters. There are total 82 multiplied by 82 gray matter pairs cannot be shown here. So then this we show how it look like this. So in these gray matter pairs, and there are non-common components. These non-common components in the gray matter pairs shift the triple-wise correlation value across all wet matter bundles. Yeah, so you can find this is only this gray matter pairs will have correlation with all the wet matter bundles. So it shifts all the wet matter bundle in the same degree, and the difference in this non-common component in each gray matter pairs will cause the common pattern of the 2D graph across all wet matters. For example, if this non-common component is higher, it will reduce the triple-wise correlation across all wet matter bundles, will decrease the mean value. If this non-common component is smaller, it will increase the triple-wise correlation across all wet matter bundles, so increase the mean value. So this causes a common pattern. So this shows the diagram of the 1D plot. Similar to the 2D graph, it shows the distribution of this relative size of the common component to the triplets for all wet matter bundles through a certain gray matter pairs. Similarly, we study how the non-common component influence the 1D plot. And we choose this direction, the 1D plot, and we get the mean and the standard deviation of each 1D plot across all these 82 multiplied by 82 gray matter pairs. And we get this plot. And you can find that the variation of the mean is greater than the standard deviation. This suggests the presence of common pattern of the 1D plot across all gray matter pairs. Similarly, so here is a non-common component. So the non-common component in wet matters shift triple-wise correlation values across all gray matter pairs. So difference in these non-common components in each wet matter cause a common pattern of the 1D plot across all gray matter pairs. For example, if this non-common component in this wet matter is larger, it will decrease the triple-wise correlation across all gray matter pairs, so decrease this mean value. And if this is smaller, it will increase the triple-wise correlation across all gray matter pairs, so increase this mean value, and thus cause the similar pattern across all gray matter pairs. So since we have a publication showing that the wet matter has quite a different HRF from each other. So the quite different value from these non-common components may cause more severe variation of these mean values. So that may be why this variation of mean is bigger than that in the 2D graph. Okay, so this is our this is in agreement with the signal model that it not only reflects the common component among the 3 functional units, but depend on the non-common component. So the common pattern further suggests that the triple-wise correlation is not specific to the common, or we call it combination component. Now let me introduce how we address the issue. We use normalization to increase its specificity. So this is a 3D matrix, and for the 2D graph, we divide each 2D graph by the sum of the corresponding element across all white matter bundles to produce normalized 2D graph. Let me introduce what it can reflect after normalization. So here, for certain white matter bundles with the index k, this is a normalized 2D graph. So I and j represent the index of 2 gray matters, and k represent a certain white matter bundles, and is equal to, this is a tripwise correlation, and this is a sum of tripwise correlation across white matter, the direction in the white matter. Yeah, so for a certain k, ji and jj, it does not depend on k. So we can remove the ji and jj. So this formula will become this. Furthermore, for different I and j, you can find this formula for different I and j has a similar mathematical form to this, since wk does not depend on I and j. That means for different I and j, this will cause a shift, cause the same value to that. So cause the same value to this normalized 2D graph, but does not cause any patterns to here. That means the normalized tripwise 2D graph should have a correlation with only this and this part, but not this part. So we get simulation to validate that. We found that normalized 2D graph have a strong correlation with this part. And for comparison, we also, in our simulation, we also add dependence of the W on I and J and get a simulation and correlate and find that the correlation decreased greatly. So that suggests this is true. And to simplify the interpretation of the mechanism, we assume that the sum of all common components among the 3 functional units for all the gray matters is equal to Ij. Since Ij is a common component among a pile of gray matters. If they are common, there should be communication and should be passed through any white matter bundles. Thus, the normalized 2D graph roughly reflects this formula. So this shows the relative size of the common component among 3 functional units through a certain white matter bundle to the common component between a pair of gray matters. Okay, so here is a diagram to show the normalized 2D graph. We remove the non-common components. So it shows the relative size of this common component to this common component among this pair, between these gray matter pairs. And similarly, so this normalized 2D graph reduce all this non-common component. It may increase the specificity to the communication as all these are communication part. Now, let me introduce how we increase the specificity of the 1D plot. So for the 1D plot, we divide it by the sum of corresponding tripwise correlation value across all the 82 multiplied 82 gray matters to produce a normalized 1D plot. So similarly, here's the formula. For a certain pile of gray matter with a certain index I and j, so here's normalized 1D plot. 1D plot is a 1D matrix. This is a index of different white matter for a certain pair of gray matter with index ij. So this is the formula with the tripwise correlation. This is the sum of the tripwise correlation of all the gray matter pairs, 82 multiplied by 82 gray matter pairs. Similarly, for certain I and j, wk does not depend on I and j, so it can be removed. And then we get this formula. And for different k, we get similar mathematical form to this for different k. That means this shift out the value in this normalized 1D plot, but does not cause any pattern in this normalized 1D plot. That means the normalized 1D plot should have correlations with only this and this part, but not this. So we get simulations and find indeed normalized 1D plot have strong correlation with this. And similarly, we also get some simulations by adding the dependence of J on K, and the correlation decreased greatly. To simplify the interpretation of the mechanism, we assume that Iijk is roughly equal to WC. So here, the WC means the communicating component in the white matter. Since all this is related to the signal in the gray matter. If a signal is only in white matter but not in the only in the white matter but not in the gray matter, that's not, we term them as non-communicating component. It's only the local signal component in the white matter bundle, like the HRF or the local signal or functional signal. So that's a normalized 1D plot roughly reflect this formula. It reflects the relative size of the common components to the only communication part in the white matter bundle. So this is a diagram to show the normalized 1D plot. Compare with 1D plot with not normalization, you can find that the area function, the signal area in this white matter become smaller. So this part shows the non-communication part. So we remove this non-common component, non-communication component in the white matter. Okay, so by using normalized triple-wise correlation, we can provide network which we call communication network, since it's more sensitive to this common pattern, the combination part. Then we reprocess the mean and standard deviation of the plot I show above, but for the normalized 2D graph here and normalized 1D plot here, we found that the pattern disappear. So that means we successfully removed the common component, and also this this suggests that maybe rich information in all these plots. Okay, now let me introduce some applications. So here we have a healthy group subjects with age 20 years old, and here we have conventional gray matter correlation networks. And here is for the normalized 2D graph for genome of corpus callosum, GCC. And this is normalized 2D graph for BCC. And this is a normalized 2D graph for SCC. And in this network, the green lines represent the connection between gray matter pairs. And we only choose the top 5%. And the red sphere represent the hubs. And the red shape represent the corresponding white matter. So although the functional connectivity is not necessarily to overlap with the corresponding white matter bundles, but we found that they roughly overlap. Okay, so here's for different ages. So we have age from 20 to 70. We found that for this is BCC, we found from 20 to 50, the network nearly no change. But for 60 to 70, the network moved to the frontal lobe. This may suggest that the white matter, the function of this white matter bundle become weak, and frontal lobe they compensate these connections. And we also study the AD, and this data haven't been published. And this is also for BCC, for elder people but it's healthy. This is still the connection is in the frontal lobe. But when in the early MCI to AD, we found the connections come back to overlap with the white matter bundle, but become more randomly distributed. That may be in early MCI, even the frontal lobe, the function in the frontal lobe become weak, and so the connection come back, but this is also weak, so it become randomly distributed. Now let me compare with conventional networks. So this is conventional green matter networks from age 20 to age 70. Although a lot of reports show that there's a change of the amplitude or any other metrics in the green matter correlation metrics. But here, from the whole structure, we cannot directly see the changes. This is a 2D graph that is for BCC without normalization. For age 20 to age 70, we can find that from 20 to 60, there's no change, but for 70, it moved to the frontal lobe. So here we show the three map for BCC from age 20. And this is normalized 2D graph. This is a 2D graph without normalization. And this is a green matter correlation map. So from our signal model, so the quantum green matter has should be skewed by the non-common components. And the 2D graph without normalization, we improve the specificity to a certain white matter bundles, but still skewed by the green matter non-common component in the green matter pairs. And for the normalized 2D graph, we remove the non-common components. So you can find that it have different networks. And so for our study in this different age, we found the normalized 2D graph is sensitive to age, and 2D graph weakly sensitive to age, since it only shows change at 70. And green matter is not sensitive to age from the whole structure. And thus, we assume that it's common, or we call it communication component, is sensitive to age, but not the non-common components. So that's why the normalized 2D graphs are more sensitive to age. We also compare with conventional green matter correlation map and white matter correlation map. So similarly, from the whole structure, we cannot directly see significant change. Okay, so the above is the 2D graph and normalized 2D graph. Now let me introduce 1D plot. So this is from the other direction of the 3D matrix. So this shows the mean and standard deviation of the z-score of the normalized 1D plot. We cannot see any pattern here, similar to what I introduced above. So this is the mean across all these 82 multiplied 82 green matter pairs. And we use k-mean clusters to separate those different 1D normalized 1D plot. And we found that when the k is 7 or 8, the sum distance is greatly reduced. Here we show the 8 clusters we got, and we found that the pattern come back. And we draw the clusters, 8 clusters on this 2D matrix and get this. So in this different color represented different clusters. So number one represent those clusters. Yeah, so they have similar pattern. What's the meaning of this? I will introduce in later slides. Okay, so now let's compare with conventional green matter. So here show the histogram of conventional green matter correlation values from the 8 clusters that we separated by using the normalized 1D plot. We found that the overlap is difficult to separate them from the histogram of the green matter correlations. So let me introduce why. So here's a 1D plot for one gray matter pairs, gray matter number 1 and number 2. And we have all the white matter bundles from 1 to 4 just illustrated. We use 4 to illustrate all white matters. And here's a 1D plot represent the I for the gray matter 1 and 2, and for the white matter 4, and normalized by the signal component in white matter number 4. This is another 1D plot from gray matter number 3 and number 4. So this value corresponding to this, it represents the I for gray matter 3, 4, and for the white matter number 4 over the signal component in this white matter. So if the I12 is equal to I34, we can get from this formula that the 1D plot is the same. Conversely, if the 1D plot from gray matter number 1 and 2 to the 1D plot from gray matter number 3 and 4, it's highly possible that I2 is equal to I34. Or there may be some more complex mathematical relationship, but this should be strongly related. So this suggests that in each cluster, the combination part may be more close than that in different clusters. Well, for the conventional gray matter correlation, so similarly, this shows gray matter pairs number 1, number 2, this gray matter pairs number 3 and the number 4. So the correlation, the pairwise correlation, this shows the common component I12 over over J12 of this component. This similarly, this show I12, mistake, I34 over the all component in this 34. If I12 is equal to I34, this should be I34. It's not necessary for the gray matter correlation to be the same. Thus, so we found that the histogram overlap. So this may be the non-common components in these gray matter pairs. They vary substantially more than in each cluster, more than that among different clusters. So this suggests that only from gray matter correlation, we cannot separate clusters, but by removing the non-common component that vary substantially in different gray matter pairs, we show the common component, and this common component can be separated into different clusters. And in this cluster, they are more close to each other. Okay, we also compare our method with the conventional network clustering. And here we choose the diagonal of the 2D matrix. So the red line here. That shows the true correlation of the gray matter and its gray matter itself and the white matter. And based on the clustering on this diagonal, we draw this map. And from this map, you can find that most of cortical area match Yau's network clustering, especially in the region close to motor network, visual network, and default mode network. Okay, so we only show the diagonal, but there's other part that may be other networks that we need to discover. Okay, so in summary, so we show the traditional pairwise can be reflected by those part. It reflects the distribution of the relative size of this common component to each pairs for all these gray matter pairs. And for the triple-wise correlation, we increase the specificity to 1 white matter bundle. So it shows the correlation among the 3 functional units for all these gray matter pairs. And for normalized triple-wise, we remove the non-common component it shows the relative difference of relative size of this common component to the common component between a pair of gray matters. So it only related to communication component, the relative size of this communication components. Okay, so the functional network have a non-communication component. The correlation, strong correlation may only reflect the similarity or association of this pair of functional unit. But for the combination network, we remove the non-common component. So it should be more sensitive to the combination part. The combination network we separate into two type. One is normalized 1D plot. Here we assign a meaning for this. So the normalized 2D plot reflects the relative engagement of the selected white matter bundle with different pairs of gray matter, such that higher value in the matrix suggests specific pairs communicate via the bundle more extensively than via other bundles. Well, for the normalized 1D plot, it shows how communication between pairs of gray matter areas is distributed across different white matter bundles, and higher values imply that the selected white matter interacts more than this pair of gray matter than other pairs. Okay, so take-home messages. In other words, we gradually increase the specificity of brain network to combination components, which could potentially act as a sensitive indicator in neurobiology. Okay, so yeah, that's my talk. Thank you for my co-authors and grant support, and also thank you for your attention.